So the next example is known as a pitchfork bifurcation. And the example that I'm going to use for the O to E here is going to be y prime is equal to y minus 1 times a minus 1 minus y minus 1 squared. And this has equilibrium points when y equals 1. Y equals 1 is always an equilibrium point because this always makes this equal to 0. And when a minus 1 minus y minus 1 squared is equal to 0. And we want to I'll use lambda here to be consistent with my other notes. And this equation only has solutions when lambda minus 1 is positive, or when lambda is greater than 1, greater than or equal to 1. And the solutions that it has are given directly by y is equal to 1 plus or minus the square root of a minus 1. Just solving this quadratic for y in terms of lambda. So what we're seeing here is that if lambda is less than 1, we have one critical value, and the phase line looks like this. So this is y equals 0, y equals 1. So we have one critical value at y equals 1. And if you take y less than 1, this function is going to be positive. And if you take y greater than 1, the function f is going to be negative. So this is what the phase line looks like for lambda negative. On the other hand, when y is positive, we're going to have a slightly different picture. And when y equals 0, we're going to have a slightly different picture. no matter what, y equals 1 always remains a critical value. But if lambda is 0, we'll see that we still have one critical value. Sorry, so if lambda equals 1, not 0, we'll still have one critical value. And this expression will be negative y minus 1 squared, which is going to be negative times y minus 1. So this will still be positive when y is less than 1, because you get negative times negative, which is positive. And then when y is greater than 1, it will be negative. So even at lambda equals 0, this 1 remains an asymptotically stable equilibrium value. But the interesting thing about the pitchfork bifurcation is that when now lambda is positive, you go from having one stable critical value to having three critical values. One critical value at, call it, I'll call these two roots y1 and y2. The negative root being y1 and the positive one being y2. So you go from having one critical value, one stable critical value, to having three critical values. And if you look at the value of f in each one of these regions, f is positive to the left of y1. It'll be negative to the right of y1, but less than 1. It'll be positive to the right of 1, to the left of y2, and it'll be negative to the right of y2. So the pitchfork bifurcation is when we go from having one critical value to having three critical values, and the stability of these is changing. Right? One's going from being an asymptotically stable critical value to being an unstable critical value. And these two new critical values that pop up, y1 and y2, are both asymptotically stable. So these are what the phase line diagrams look like for this bifurcation problem. And we can go through and really see what's going on here and why this is called a pitchfork bifurcation when we look at the bifurcation diagram. So we always have a critical value here at y equals 1. Oops, sorry, and I wrote lambda equals 0 here, but I should have wrote lambda equals 1. I apologize for that, it's just a typo on my part. So here at lambda equals 1, we have the appearance of two new critical values for any value of lambda greater than 1. And if you plot out these curves right here, the curve y equals plus and minus the square root of lambda minus 1, this is just going to be a quadratic opening or parabola opening. like this, and a parabola opening like this. Oh, and I should do those in bold so you really see this curve. And this is why the pitchfork, or how the pitchfork bifurcation gets its name. Because this looks like exactly like a pitchfork or a trident. And in this region up here, f of y lambda is going to be negative. In this region down here, f of y lambda is going to be positive. And what we're seeing is that across this region right here, f of y lambda goes from being positive to being negative. So for any fixed value of lambda less than 1, you're going to recover exactly the phase line diagram that we talked about before, where f of y lambda is negative here, so the function is decreasing, and f of y lambda is positive here, so the function is increasing. And this holds all the way up to and including the point lambda equals 1. But then when lambda is greater than 1, you get a switch. Alright, this is still negative in this region, but it's positive in this region right here. It's negative in this region right here. And it's positive in this region right here. So following the convention that we introduced before, this now becomes a dotted line, or a dashed line, because this line is representing an unstable critical value or equilibrium point of our differential equation. So the pitchfork bifurcation is very interesting because of the fact that you have one critical value, an asymptotically stable critical value that switches into an unstable critical value, and you have the appearance of two new critical values to your differential equation. So just like before, we can take a look at this using Desmos and GeoGebra to kind of shed some light on what's going on, get a better visualization of what's going on. In Desmos, we're seeing exactly what I just drew as we cross 1 right here, the point lambda equals 1. You have the appearance of two new critical values, and the type of critical value for y equals 1 changes. It goes from being asymptotically stable to unstable, along with two new stable equilibrium points that appear. And if we look at a plot of this, this is exactly what we see. So this blue surface right here is the function z equals f of y lambda. And you see that this is why all of these points are stable, asymptotically stable, because it's the function is positive in this region and it's negative in this region right here. But at the point lambda equals 1, this is the lambda axis and the y-axis, when lambda equals 1, this function switches its behavior, but you get this region here where the function goes from being positive to positive and then back to negative. And this explains why at this critical value, or at this point 1, you get a change in the characteristic behavior of solutions. I think it very clearly explains why this happens. So all of these are common bifurcations that we actually see in applications, various applications. And the next example is probably one of the most complicated out of all the examples we're going to look at, but it's also very common to see in real-world models. And this is the example of what's known as hysteresis. And to show what hysteresis means, we'll look at the example y prime is equal to lambda plus y minus y cubed. Oh, and let me turn on the notes right here. So hysteresis is a very common phenomena that we see in many, many different applications, but it's quite a complicated phenomena. We'll use this example to illustrate exactly what we mean by hysteresis. So just like before, we know that this is going to have equilibrium points when lambda plus y minus y cubed equals 0, which is a general cubic equation or cubic polynomial equation. You can rewrite this if you want as when lambda is equal to y cubed minus y. And there is a cubic equation that we can use to solve exactly for y in terms of lambda, but it's a little bit complicated to use, so I'm not going to use it here. I'm just going to note that for special values of lambda, we can solve this exactly, very, very nicely. So if you want to go through and use the cubic equation here, you're welcome to do so. However, it's going to get a little bit complicated. So we'll just look at when lambda equals negative 2 over 3 square root of 3. We have two special solutions. And this is going to be directly verified. Solutions are going to be y. And I'm going to number these specifically. We'll say y3 is equal to 1 over the square root of 3. And y1 is equal to negative 2 over the square root of 3. And when lambda is equal to 2 over the square root over 3 times the square root of 3, we have two other solutions. y2 is equal to negative 1 over the square root of 3, and y4 is equal to 2 over the square root of 3. So the phase line diagram for this example has to be split into all these possible values of A. Or of lambda. So when lambda is less than negative 2 over the square root of 3 times 3, and we put 0 here, and we'll put a spot for y1, a spot for y2, a spot for y3, and a spot for y4 on this diagram right here. So when lambda is less than negative 2 over 3 times the square root of 3, there's only going to be one root to this, or one real root, I should say, to this quadratic or cubic polynomial. Call that YR1. And when this is the case, if we have one equilibrium value, you can use the cubic formula to calculate this equilibrium value. There will be two other roots to this cubic polynomial, but they'll both be complex, so they're not real values. So for values of y less than yr1, this function is going to be negative. And for all values of y greater than r1, this function is going to be positive for all values less than r1 and negative for all values greater than yr1. So the root of this polynomial when lambda is less than y1 is going to be an asymptotically stable equilibrium value. And we're going to have to make multiple copies of this without these values here. So let me just erase these values for the arrowheads here. And we'll copy this picture. We're going to have to copy the picture a couple different times. One, two, three, and one more. So when lambda is equal to negative 2 over 3 square root of 3, we've seen that we have two solutions, y1 and y3, so two equilibrium values. And if y is less than y1, f of y comma lambda is positive. When y is greater than y1 but less than y3, it's negative. And when y is greater than y3, it's also going to be negative. And you plug into this function right here. So we're going from having one stable equilibrium value to now having two equilibrium values, one being stable and the other being unstable. When lambda is between negative 2 over 3 root 3 and positive 2 over 3 root 3. We'll actually have 3 real roots to this equation. You can go through and use the cubic formula to show this. That when lambda is between these two values, this equation has 3 real roots. And the real roots are going to, generally be greater than y1, less than y2, one root that's going to be greater than y2 and less than y3, and one root that's going to be greater than y3 and less than y4. So you can call this yc1, yc2, and yc3. So this is for any value of lambda in between these two values. You can show this using the cubic equation. And the idea, though, is that when y is less than yc1, you have that the f function is positive. When y is between yc1 and yc2, you have that it's going to be negative or decreasing. When f is between yc2 and yc3, you have that it's going to be positive. And when y is greater than yc3, it will again be negative. And this is the case until lambda reaches positive 2 over 3 root 3. In which case, as we saw before, and it's easy to go through and check this, when lambda equals 2 over 3 root 3, we have two roots, y2 and y4. So we'll have two critical points, two equilibrium points, where when we're less than y2, the solution is increasing. When we're greater than y2, the solution is also increasing. And for initial conditions greater than y3, the solution is decreasing. Oh, no, not y3 here. Sorry, y4. I highlighted the wrong value. So y2 is an unstable critical point, or equilibrium point, and y4 becomes an asymptotically stable equilibrium point. And then the last situation here is when lambda is greater than 2 over 3 root 3. In which case, we'll have one root, call it yr2, and for any value of y less than yr2, y prime is going to be positive. And for any value of y greater than yr2, the y prime value is going to be negative. So we have, back to the initial case we started with, we have one equilibrium point which is asymptotically stable. So this is by far the most complicated of the examples that we've seen of bifurcations so far. It's going to pay to look at the bifurcation diagram and dissect it. To see what insight it provides us into this hysteresis phenomena. And if we immediately go and we plot out what this is going to look like, the curve that we're plotting is the level curve a plus y minus y cubed is equal to 0. Which corresponds to a cubic curve, which opens, we end with lambda, not a. So it's a cubic curve opening along the lambda axis, and it looks like this. You can do a little bit better. This is what our curve looks like. And we can see that immediately this phenomena is directly explained based on this level curve. Because in this region, the region to the left of this level curve, the function is going to be negative. And to the right of this level curve, the function is going to be positive. And we see very clearly what was found before if we draw out some sample fixed values of lambda to investigate this. By the way, those special values for lambda are right here, correspond to this point right here, and correspond to this point right here. So this is negative 2 over 3 root 3. And this is positive 2 over 3 root 3. So when lambda is less than negative 2 over 3 root 3, you have one stable critical value. The function is decreasing here, and it's increasing here, because in this region f is positive, and in this region f is negative. It's positive here and negative here. at the switching point, negative 2 over 3 root 3, we have the appearance of a new critical value. The function's still negative here. And it's negative here. And it's positive here. So these 2 points correspond to our critical points. We have 2 critical points for lambda equals negative 2 over 3 root 3. When lambda switches to be between negative 2 over 3 root 3 and positive 2 over 3 root 3, we have a switch where function's still negative here, but it's positive here, and it's a negative here, and it's positive here. So you have a switch where you have now 3 critical points for the differential equation, and the stability of the outer 2 critical values is that they're asymptotically stable, and our inner point becomes, well, it's unstable here and it's unstable here. This corresponds to 2 critical values, whereas when it lambdas between these 2 numbers, you have now 3 critical values. And that holds all the way up until you get to lambda equals positive 2 over 3 root 3. Where you have that f is negative here, it's positive here, and it's still positive here. So this is an unstable critical point, which is exactly what we saw before, and this is a stable critical value. And the last case is for positive lambda, where we're back to having 1 critical value that's asymptotically stable. So by the convention that we introduced before, that means that this section of our curve, the middle section of our curve, is completely unstable. So we'll draw this as a dashed line. Or dash curve. Because it's representing critical points that are unstable. And this is what a bifurcation diagram looks like for hysteresis. So just like before, if we go take a look at this in Desmos and GeoGebra, so using those 2 tools, you see that this is exactly a plot of this curve. As we move our value of lambda, eventually we get to this point right here, which is where 1 stable critical value turns into 2 stable critical values, or two critical values. 1 is stable and 1 is unstable. And this then now switches into having 3 critical values, 1 stable, 1 unstable, and the third one stable. And then as we increase to this point, we have 2 critical values again, 1 stable, 1 unstable. And then for lambda positive, we have that solutions are characterized by just 1 critical value. And on our 3D plot of this, it's very, very well explained. If we plot the surface plot of this function, the function z equals lambda plus y minus y cubed. You see that in this region right here, this is the lambda axis again, this is the y-axis, and plotting this function gives you a curve or a surface plot where in this region the function's negative, in this region the function's positive, and it directly explains the behavior that we're seeing here. But we've done all of these examples without actually going through and solving the underlying differential equation. And that's kind of the point of this bifurcation analysis, is to go through and be able to understand how the solution to a given differential equation is going to behave without going through the process of solving the differential equation. And we'll see that the analogs that we'll develop for systems are going to be very, very powerful. So using GeoGebra and Desmos, we can go through and get a very nice picture of what's going on here. So for negative value, or for values of lambda less than negative 2 over the square root of 3, you see there's one critical point, or one equilibrium point of our differential equation. And then at the value lambda equals negative 2 over this 3 times the square root of 3, you get that one critical value turns into, we have two critical values. One is stable, one is unstable. And then when lambda is between negative 2 over 3 root 3 and positive 2 over 3 root 3, you have the appearance of three critical values of our function, and you have a loss of stability in the middle one. The middle one is unstable. The other two are stable, and that happens all the way up until lambda equals positive 2 over 3 root 3, in which case you have two critical values again, so we go from 3 to 2. One is stable, one is unstable. And then for values of lambda that are greater than 2 over 3 root 3, you have, again, one critical value, which is a stable critical value. So this is probably best seen when we visualize this as a surface plot. And you see here, the x-axis is this red axis, the lambda axis is this red axis, the y-axis is this green axis, and this is a surface plot of the function z equals lambda plus y minus y cubed. So you see exactly what we said before, that this function is positive in this region, it's negative in this region, and this level curve is separating these two regions from one another. And this exactly explains, as we talked about before, the qualitative behavior of the solutions to this ODE. And what's amazing for all of these examples is that we haven't gone through and solved a single ODE. We went through and just using the differential equation itself and a little bit of knowledge of multivariable calculus, been able to classify the critical points and the behavior of solutions to the ODE for the entire range of its parameter space, or the entire range of its parameters. So the last example I'll look at is the logistic equation, and this is going to be the non-dimensionalized form of the logistic equation. Y prime is equal to lambda 1 times y times 1 minus y over lambda 1. And we can split this into multiple different parts after we solve for the equilibrium points. The equilibrium points occur when oh, not lambda 1 here, sorry, lambda 2. Either y equals 0 or y equals lambda 2. So this means that our phase line diagrams are going to be a little bit more complicated. We have to go through and look at multiple scenarios. And what makes this slightly complicated is that we have two parameters now. So we have to look at when lambda 1 is negative and when lambda 2 is negative. We have to look at when lambda 1 is equal to 0 and lambda 2 is negative. We have to look at when lambda 1 is equal to 0 and lambda 2 is positive. And lastly, we have to look at when lambda 1 is positive and lambda 2 is negative. And when lambda 1 is positive and lambda 2 is positive. Oh, and I'm forgetting one. We also need to look at when lambda 1 is negative and lambda 2 is positive. So in any case, we're always going to have that y equals 0 is a critical value. Then when lambda 2 is negative, that means that y equals lambda 2 is a critical point. When lambda 2 is positive, that means that y equals lambda 2 is a critical value. You have the same picture here. And then the same thing here. And this is lambda 1 equals positive and lambda 2 is negative. This is when lambda 1 is positive and lambda 2 is positive. So when lambda 1 is equal to 0, this is it for the phase diagram, because if lambda 1 equals 0, y prime equals 0. So we really have no change, which means there's going to be no arrows on the phase line diagrams for these two cases. However, for lambda 1 negative and lambda 1 positive, the phase line diagrams are going to be switching up and changing depending on the various values of lambda 2. So visualizing this, in the phase space is going to involve a function of 3 variables, not just 2 variables. So lambda 1, lambda 2, and y. So it's a little bit more complicated to do a bifurcation diagram and to visualize this like we visualized it before. But trust me, it's definitely possible, and you can do it for a function of 3 variables. If you go to any higher degree function where you have more parameters, it's not super easy, which is why the phase lines are probably the best way of visualizing the behavior of this function. But you see, if we kind of let's take a look at this for a couple of these different values. So our general solution is going to take this form where R is our lambda, and this will conclude today's lecture. Thank you so much for tuning in, and I hope you have a great day.